Hi everybody, I'm Matteo Sinerchia from Italy, and my talk will be on the integration of new lab-based equations to model the metabolic response of one fish and one invertebrate species to temperature changes induced by climate change. This work was done under the European project Pandora, which was funded by Horizon 2020, the main objective of which is to integrate new biological knowledge into models to improve the projection of changes in fisheries resources. Our study area is the Strait of Sicily, which is located in the Mediterranean Sea, and it is characterized by a very complex ecosystem, and it's really important because it hosts the biggest Italian fisheries with lots of employment to fishermen. This is the project in its whole, and basically it was a first part that involved the stakeholder engagement with discussion, iteration to decide which are the scenarios of interest. Then that was followed by some lab experiment to get the physiological equations that we then integrated into the model. We applied to their physiology of the two species of interest, and we ran the scenarios which we then show to the stakeholders at the end. So the Atlantis model domain is divided into 37 boxes, and it is forced by the output of the Polcom RSEM model run by PML that provides us a time series for temperature and salinity from 1980 until 2100. The biological community is composed by 58 functional groups, 26 of which are as vertebrate, and 8 target species left at species level, while the fisheries sector is represented by 8 different segments, different fleets. So the first part of the project involved some meetings for stakeholder engagement to discuss critical issues and discuss scenarios of interest. And during this meeting, one question came out about how climate change was affecting marine species of the area, and in particular red mullet and Norway lobster. They are both two commercially important species fished in the Strait of Sicily. To answer this question, a set of lab experiments was set up, during which red mullet and Norway lobster were kept in an acclimation tank at different temperature for 1 month, and then they were put into respirometers to measure their oxygen consumption under different temperature and activity level. From this we derive the physiological equations that describe their, let's say, wellness at different temperatures. The concept that we use is the one of aerobic metaboliscope, which is really describes how much fuel, how much energy they've got in their tank. And to calculate it, we measure two variables, which is standard metabolic rate and the which is shown with the dotted line, which basically just increases with time, with temperature, and then the maximum metabolic rate, which is the maximum activity they can sustain at different temperatures, which goes up to an optimal level and then goes down. And there are two ways of looking at the aerobic scope, and there are two formulations. One is the absolute aerobic scope, which is basically the difference between the two, as you can see in here is the black line, And there is also the factorial aerobiscope, which is instead the ratio between the two. In these plots we compare the absolute aerobiscope and factorial aerobiscope for the two species. On the left the Norway lobster, on the right the red mullet. As you can see, for red mullet the two formulations have got a similar shape and coincide with their optimal value being found at 21 degrees, while for nephrops it's not like so, and the two formulations have got opposite trends. While the absolute aerobiscope increases up to 19 degrees and then falls, the ratio between the two variables, so the factorial aerobiscope, decreases with temperature, and he found his peak at the lowest temperature of 10 degrees. So to describe these two trends, we use for the absolute aerobiscope, the formulation from the cardinal model equation from Russo, and while for the factorial aerobiscope that we use for nephrops, since we know that nephrops is a boreal species and is never found in the Mediterranean at temperature above 17 or 18 degrees, we used the factorial aerobiscope formulation described by a polynomial function. So then we had to integrate these informations in our model. So the first thing that I had to do was to turn Norway lobster as from an invertebrate to a 7 stages vertebrate. So it has got 7 age classes. That's just a technical way to divide it into different stages. And then what we did was basically create alternative Q10 methods for our species, and we substitute in the code our functions. So for aerobiscope, Q method 2, and for factorial aerobiscope, method 3. And we applied those to the different to our species. We then basically what we did was to create a temperature scalar of the growth rate, so our mum, and then we run the simulations until 2100 under two climatic scenarios, the RCP 4.5 and the more extreme RCP 8.5 scenario. So this just shows the difference for each in time between the two scenarios, showing that the 8.5 has got a much harsh increase in temperature. Note that the scale in here is different. These are different water levels, and but there is a big increase after year 2065. Also, we applied some harvest controls rule. We integrated those for red mullet, which is not overfished, and for Norway lobster, which is slightly overfished. We created 7 scenarios in which we have got basically from constant mortality, fishing mortality, to changes in levels of fishing mortality, MFC. So these are the time series of the simulations, and in red we see the observation that we have got, and both for red mullet and for Norway lobster, we see that both the biomass and the catch are trends are captured by the model. And also for we don't have this information for nephrops, but for red mullet we see in blue the observed distribution of biomass into age classes, and in orange the simulated by Atlantis. So also that is quite close. This is an average for the period of observation 2006-2017. Well, this is not very clear, but is basically the biomass, the relative biomass for the different groups, and they are mostly quite stable, apart a couple of invertebrate groups that goes up a little bit, but it's generally quite stable. So then we run the scenario for the different fishing mortality level and climatic change regime. So the different colored lines show different fishing mortalities. So with the F1 being the current mortality kept constant in time, F2 represents doubling, F0 dropping to zero fishing mortality. So it's quite clear that biomass is mainly controlled by fishing mortality, and you can see that there is a slight decrease in biomass with time, but it gets for both climatic scenarios, but it gets much sharper from year 2000 between year 2060 and 65, as you can see from the difference of 6,000 biomass for the closure, complete closure scenario. And catches in the short term, doubling the catches would greatly increase the catch, obviously, but also will provide the biggest decrease in biomass. But in the long run, it doesn't seem to be the optimal level, while an intermediate level would be more sustainable and productive. Yes. While for red mullet, basically there is really no effect of temperature, and it just can be seen that the biomass is mainly controlled by fishing mortality. We also made a simple economic assessment of the different scenarios, and we consider the profits as the revenue minus the cost, and the revenues we calculated as the product of the catch times the value of the catch, and for cost we considered fuel, salaries, and fixed cost. And fuel and salaries, we link them through some correlations that we have from fishing observation data, the link fishing mortality to number of fishing days. So we then applied some one future scenario of increase of price in fuel in blue line, and the value of the resources in orange. This plot show the different profits under the different fishing mortality scenarios. This is for the most extreme climatic scenario, the 8.5. Basically shows that red mullet is underfished, while it's not overfished. So it shows that there is some room for expansion of the fishery in the future, but probably it becomes uneconomical due to high increase in fuel cost. While for Norway lobster, from 2060 it becomes totally uneconomical to fish. To conclude, this method is interesting because it provides us with sound physiological equation which are based on lab experiments that are reproducible. The negative side of it is that it can be applied to few species to such a definition level, and it would be really interesting for me to discuss ways to extend similar approach two other groups in a more abstract way, similar to what Bossier et al. Did for the Baltic in 2021. And also, it would be interesting to know how, well, if it's possible, and how to implement temperature-dependent movement in Atlantis, and also if it's possible to provide a trophic closure for some applications in which we have got some top predators migrating in and out of the model domain, but coming back with always with the same sites year after year. Thank you very much and goodbye.